Okay, so here's a new topic for today. So kind of a new topic. So it's line integrals. We've already seen a little bit of this. So you may recall we've already talked about surface integrals, and when we talked about surface integrals, we talked about this idea of domains that are sort of dimensionally out of place, right? A surface is a two-dimensional thing, but it's in a three-dimensional world, and what do we do with that? And we talked about two such ideas. The other one being a curve, a one-dimensional thing that's in a two-dimensional or three-dimensional context and thus out of place, and what do you do? So the first part of this argument we've actually already kind of built up. We've already talked about how, this undesirable domain, undesirable because of its dimension. You can pull it back, right, through parameterization. You can pull it back to an interval, here on the t-axis, which is a one-dimensional region in a one-dimensional world, exactly like we like them, right? And and then we developed a little bit of the details. We talked about how, some little piece of the curve here, some little piece of curve like that. Well, that's too small. Let's redraw that picture like this so we can see it better. And we can approximate the length by way of this position differential vector, dx, right? And dx is v dt, easy to motivate. And from there you can compute ds, because ds is just the magnitude of that dx vector, right? Thus giving you your stretching factor. So all of this we did as a kind of a segue into how would we do something similar on surfaces. So you can flip, I think it's about 15 or 20 pages back in the notes. You can flip back and see how we've already done all this. The book makes a choice that I've already mentioned, I think is weird, but fine. It's whatever. It's subjective. Everybody's got their own sort of choices on how to do these things. And they abandoned the one-dimensional question and decided to pursue first the two-dimensional question of surface integrals. Right? We developed surface integrals. And only now comes back to doing the one-dimensional example. So anyway, whatever. So here we are. We've already got this development done. And now let's just kind of take the last step into the end zone here. Now that we know what ds is v dt, right? As developed several days ago. When you pull back that integral, well, don't forget pulling back through the parameterization. A point x on the curve is now a function of t, right? And so this line integral, this integral defined on a curve in space, I can now rewrite as a good old plain old Math 111L single variable integral. Right? It's an integral on an interval on the t-axis, is world's easiest kind of integral. Okay. So again, we were almost there, but just hadn't quite put the finishing touches on it. Okay, so this is our formula. Don't forget, again, the big idea here is that ds, the size of a piece of the domain, relates to a size of the piece of the on the t-axis by way of this stretching factor. Right? V. So this is a formula you have to remember when you're talking about pulling back through a parameterization of a curve. The stretching factor is speed, the magnitude of the velocity vector. Okay. All right. So let's do a bunch of examples. I'm going to do kind of a bunch of examples all at once because we're talking about how to do a pullback of integrals. So I'm just going to pick one curve and then talk about how on this one curve you can pull back all these different kinds of applications of integrals that we've already talked about at this point. So here's our curve. So it's parameterized like so. Now I've phrased this question with the parameterization given, right? The parameterization won't always be given. Thus is the question, how do I parameterize a given curve? There's a nice trick for it. The graph parameterization is what I've done here. You can probably notice that every point on this curve has the feature that y is x squared. And the graph parameterization trick that we did for surfaces, same trick works here. We'll talk about that more later. But anyway, just to focus on how to actually do a pullback, we're going to take this parameterization as given. And that curve, t goes from 0 to 1. Suppose that on that curve, this is how mass is distributed. Mass per unit length is given by this formula. And let's, with that given, let's compute the mass of this thing. Let's compute the location of the centroid of this thing. Let's compute the moment of inertia around the x-axis of this thing. These are just a bunch of integrals. Of course, all of these integrals have the same domain, right? The domain is the same curve. Therefore, for all of these integrals, I'm going to pull back through the exact same parameterization, right? And the only thing that's different is the integrands. So, all right. So let's see the details. We'll start with mass. How do I compute mass? Well, old news. Chop it up, add it up. Total mass is the sum of a bunch of little pieces of mass, and mass per unit length times length gives you little pieces of mass. So hopefully everybody remembers that. So what is ds? Well, ds is v dt, which is that. Now, where did those details come from? What is v? Well, v is the magnitude of the velocity vector. The velocity vector is just an easy, you take the derivative of the parameterization, that gives you your velocity vector. Magnitude of the velocity vector, easy calculation. All right, so that v is right there. Everybody good so far? All right, so now let's talk about the this density. What are we going to do with density? Density is x plus y, that's given. And I say that x plus y I can rewrite like that. Now, how do I know x plus y rewrites as t plus t squared? Well, don't forget, right? Our parameterization tells us how to pull back the variables, right? Specifically, x is t. You can see right there in the parameterization, right? And y is t squared. You can see right there in the parameterization. So all I've done, in turning, this sort of immediate line integral, chop it up, add it up expression into an integral that I can crank out is really plug in with the formulas, right? Just don't forget what your stretching factor is and how to compute it. And then don't forget how to rewrite the integrand. Well, it comes directly from the parameterization. Right. Now, I'm going to go very, very quickly through the remaining integrals on this page because it's morally the same process. How would I compute the centroid? Okay, well, here's the formula for the centroid. Now, I do have to compute the mass, but that's already been done. Right? So, yeah, let's just leave that there. Here's our integral, then, that I'm interested in. Oh, and it looks like I dropped the 1 over m. Silly me. Sorry about that. Right, the 1 over m. Right there. Make that correction, please, if you have the notes printed out. Don't forget to write that 1 over m. Okay, so x dm. All right, now there's a couple of things to think about here. What is dm? I am going to have to zoom out one notch. Here we go. What is dm? dm claim is all of this. Now, why is that? Well, dm is density times ds. It's just like this, right? Density ds, which, as you may recall, was this, which was that. So that's all the same stuff, right? We've got stretching factor, just like we had before. Stretching factor times dt gives me ds, and then density times ds gives me dm. Everybody on board? Same argument as before, pretty much. So what's the difference? What's new in this integral? Well, of course, the new thing is the x right there. And x, of course, is t. Again, straight from the parameterization. So we've got a different integral, different integrand. So there's some different things to plug into, but all the process is the same idea of don't forget your stretching factor and then use your parameterization to pull back the variables. Everybody see how this is morally equivalent? Different integral, same story? Any questions? Feel free. Okay. So I'm just going to say ditto for the rest of these. It's the same big idea for all the rest of these. DM is all of this business, just like it was before in the previous ones, and then it's just a matter of interpreting the variables appropriately in the integrand. Okay. Here's a different example. Kind of a manufactured example. I tried to make something physically relatable. And so here's what I came up with. Suppose we have, this is our property, right? We've got a little circular plot of land, let's just say, just to make the algebra reasonably easy. Circular plot of land, and we want to put a fence around this plot of land. Right? And the thing is, certain parts of the yard I want to be in shade more than others, and the sun is at certain positions, and depending on these various considerations, I've decided that I need for the height of the fence at any given location to be given by this formula here. Right, so different parts of the yard, I need the fence to be higher. Different parts, I need it to be lower. Right, so reasonable question: what's the total area of the fence? Like, I need to hire someone to come out and paint the fence. How much paint are we going to need, and how much he's going to charge depends on how much area there is of the fence. So how do we do this calculation? We can't just take height times length because, well, it's not a constant height. And so really what we do is we have to do an integral. I'm going to have to say for this curve here, for every point along this curve, I need to look at a little piece of the curve. And I'm going to multiply the length, the ds of that little piece of curve, times the height at that location to get the amount of area of that little piece, and then I add up over the entire curve. So it's exactly a line integral like we've defined today. Okay, now we know from previous examples that the first thing to get is a parameterization. Everything comes from the parameterization. Right? The parameterization gives us our stretching factor. The parameterization gives us our formulas for rewriting the variables in the integrand in terms of t. Right? Everything comes out of the parameterization. So in this example, the parameterization was given, so we didn't have to find the parameterization. It was handed to us. Here, it was not. So step one, we have to parameterize. Now, this curve being the unit circle, it's easy to parameterize. Right? Y'all remember this parameterization of the unit circle from way back when? Right. Okay. So there's our parameterization, and we've already been through this part of the argument. The amount of area in a piece. You might say one plank of the fence is going to be ds times the height at that location. That gives me area. Okay. Now, to proceed, again, we need to know what the stretching factor is, so I need to know the speed of this parameterization. So we've got to go through the usual game, take the derivative. So there's the derivative of the parameterization. Right? Remember, derivatives of parametric curves are easy. Just take the derivatives of individual components, so no problem. The stretching factor is the magnitude of the velocity vector, right? And that ends up being 1. Very convenient, right? And so our calculation goes really at this point just like all the others that we've talked about. So ds is speed times dt. Our speed that we just computed, right, is 1. So ds, as it turns out, is just dt. Lucky break, you won't always get that lucky. In fact, usually you won't, but anyway, in this case, so it is. Okay. Let's see here. We are talking about height as a function of position. Now, don't forget, our parameterization was x and y are cosine t and sine t, right? So it's not so much x and y that I'm going to plug into the h function. It's cosine t and sine t that I want to plug into the h function. Reminder, here's our h function. Right, it's x plus 2 over 5. All right, so let's see here. X plus 2 over 5 becomes that when x is cosine t. Everybody on board? Yep.
It's in the 3D space.
Yeah.
How come it's not a double?
Oh, well, so one thing you could do if you wanted to compute this area, you could define, you could say, hey, this is a surface, right? And I want to do a surface integral a la section 14.8, right? I want to do a surface integral of 1 on that surface. So we would write that as, double integral over this surface of 1 ds. And then I'd have to parameterize that surface. Which, I mean, you can do that, but it's going to be harder because then you've got it's a weird surface. This isn't a graph, so I can't use the graph parameterization. It's not going to be a convenient way to sort of go about it. We're just taking a different point of view on this. We're taking the point of view that instead of thinking of adding up a bunch of areas over the surface, right? We're thinking of over the curve. For each piece of curve, we associate some amount of area. Does that make sense?
Yeah.
So yeah, so I mean, either one's fine. Either one would work. I think this one's going to be easier in this case. Yeah. Yep. Good question. Anybody else? Okay, so yeah, so at this point it's kind of all over from here, right? This is a single variable integral. Nothing to it. My usual reminder, don't forget to make sure that you're still good at all that Calc 2 integral business, right? How to do basic integrals. So this one's pretty basic, but they won't always be. Sometimes there will be weirder trig integrands. Make sure you can still do trig integrals. I'm a big believer in trig substitutions. Make sure you're good at those. Integration by parts, regular substitutions, all the usual stuff. Okay. Yes?
And if you did do it, like with a surface integral, you would get the same answer.
Yep.
Because, like, I imagine
You would get the same. Well, if you do it correctly, yeah, that's right. Yeah.
Okay.
You certainly should get the same answer. That's right. Yeah, that's right. All right. Okay. So that's what we're going to call surface integrals, at least here at this point. I'm sorry, line integral. Line integral. Y'all had me thinking about surface integrals. A line integral. It turns out, though, this is not the only kind of line integral. There is another kind of line integral, which makes you wonder, well, why? I mean, there's a different kind of lines? I mean, curves are curves. What's the big difference, right? How could we have two different kinds of integrals on the same exact kind of domain? Aren't we always just going to parameterize and pull back? And what could this construction possibly not do for us? Very reasonable question. So it has to do with how the thing that you're adding up breaks down on the little piece of curve. And it just turns out, as it turns out, there are different kinds of quantities that you could want to add up over a curve that just break down algebraically in a significantly different way, and it's going to give us a new kind of an integral. So the book, to make the distinction, uses this term, line integral with respect to arc length. I have a different terminology that I like. I like to call these scalar line integrals for reasons that I'll make clear in just a few minutes. But anyway, here comes now a new kind of line integral. I'm going to motivate it from a particular application. Here we go. So let's suppose you want to compute the amount of work that it takes to move along a certain path. So for example, let's say you're going to move along that line segment, right, from there to there, and as you go along, you're having to push with a certain force, right, that whole way along. And chapter 12 tells us the answer to this question, right? So force dot displacement. Now, specifically, think of the displacement as a vector. And we argued in chapter 12 that the total amount of work is the dot product of force and displacement. This is kind of an improvement on the old high school formula of work equals force times distance, asterisk. The force is just the component of the force in the direction of the distance that you're actually going, right? So much easier to just say dot product. Okay. Everybody remember this from way back when, a long time ago? Okay. All right, if you're maybe a little rusty, flip back to chapter 12, the appropriate section of the notes. Okay, so here's the thing. This actually makes some assumptions that we didn't really confess to at the time. We were busy being proud of the fact that we've generalized in a nice way something from high school, but we need to generalize this more now. But here's the issue. This calculation assumes that you're always pushing with the exact same force. What if you aren't? What if the force is different at the beginning and different at the end? Well, then you can't use this formula. Right? Similarly, this formula assumes that your displacement is a straight line displacement. What if it isn't? Right? Who says that we always have to move in straight lines? We usually don't move in straight lines. Right? Most roads, at least around here. Right? Hilly as it is. So what if this is your story? What if your path is a curvy path that you're moving along? And what if the force that you're applying is not always the same, right? So these force vectors are noticeably different in these different locations. How do you compute the total amount of work done? Okay, so, it looks like a hard problem. This being a class in calculus, you might be able to guess. Our strategy is going to be to chop it up, add it up, as we always do with integrals, right? So what we're going to do is say, look, grand total, there's a total amount of work that I exert. My car is going to have to burn a certain amount of gas. Well, the grand total amount of gas that my car burns is the sum of, how much gas did it burn on each of these little pieces as I make my way all the way around the curve. Right? So the amount of work is the sum of a bunch of little pieces of work. So next question, how much work does it take to move on any little piece of curve? Right? Okay. By the way, notice on this little piece of curve, all of our previous complaints go away on this little piece of curve. That is approximately straight. Not exactly, but yeah, it's pretty close. Right? Certainly in the limit, as I chop finer and finer, these little pieces of curves get more and more straight. Right? And even though the force isn't exactly constant, but it's not going to change very much over that teeny tiny little distance of this little piece of curve. So we're kind of back to a chapter 12 problem of, straight line displacements with constant forces. And so the problem looks like this, pretty much. On one of these little pieces of curve. Wrong color. On a little piece of curve, which, by the way, is well approximated by the displacement differential dx. Reminder, we already know the formula for dx. So if I displace by this amount dx, while applying this, for the purposes of this calculation, effectively constant force F, here's the amount of work that it takes to move along that little piece of the curve. And, chop it up, add it up. So we're going to add up these dWs, right? And the grand total amount of work is the sum of these little pieces of work added up over the entire curve. And so we find ourselves writing down this expression here, integral f dot dx. And so now we have to recognize at this point that's not something we've written down before. There is something fundamentally different about this expression compared to the line integrals that we've dealt with previously. Let's look back to, for example, something like this. Here, we were taking a scalar valued height, which you might think of as area per unit length of the fence, right? That scalar valued integrand we multiply by this scalar representing the size of the piece of curve. Scalar times scalar. Whereas here we find ourselves with writing down a vector valued integrand and then a vector not representing the size of the little piece of curve, but a vector representing the size and the orientation. Which direction is this little piece of curve going? It's the displacement, the displacement differential on that piece of curve. Right? So this is a fundamentally different kind of construction. This is not like the line integral that we wrote down previously. It's a brand new thing. But it's still a line integral, right? It's still an integral being done over a curve. So there's this issue of, what are we going to call this? And so you may recall I was mentioning before that I like to call these scalar line integrals. And I can tell you now why I like to call these scalar line integrals. It's because the integrand and the differential are scalars. Right? I don't think that is very creative on my part. Give me 2 seconds. I'll be right with you. So this is I'm going to call it a scalar line integral. The book calls it an integral with respect to arc length. Fine. And along those lines, you can probably guess what I'm going to call this. I'm going to call this a vector line integral because the integrand is a vector and the differential is a vector. So vector line integral, that's my terminology. Different people say it different ways. Yeah, you had a question in the back. Oh, you're good? Okay. All right. Okay, anybody else? It's good. Just a place to pause. Everybody happy? Okay, so we find ourselves again with this circumstance of, we've defined a brand new kind of Riemann sum. By the way, I haven't written this out as a Riemann sum, but you certainly could. It's limit, summation, and then, I don't want to sort of get into the notation of it, but it's exactly what you would think it is as a Riemann sum. And just like every other brand new Riemann sum that we've encountered, we don't know how to compute it. So how do we compute this thing? Right? So here's my point of view on this. Well, the main thing I don't like about this is the domain is a curve. The domain is dimensionally awkward. It's a one-dimensional thing in a two-dimensional, maybe three-dimensional context. And it's really hard to figure how you would deal with that domain. So let's do a pullback. That's how we deal with domains that we don't like. We view them as images of other things. Right? This curve that I don't like, I'm going to view this as an image of something that I do like. Right? And then we do a pullback. In the process of the pullback, of course, you have to know the stretching factor. And wait a minute, I kind of already have all that done, right? Think back to what we did here, several days ago, but then we recalled at the start of today's lecture on a little piece of curve, right? If you've parametrized, what happened there? If you have parametrized a piece of curve, right, viewing it as the image of an interval on the t-axis, then here's your development of stuff. We have this, dx is v dt, and ds is the magnitude of dx, and grand total then ds is stretching factor times dt, and the stretching factor is speed. That's where we already did all that. We don't have to do it again, right? Just like with these integrals here. It's the same construction, ds is always the same thing, no matter what kind of integral you have, right? So all the setup's been done. All we have to do is capitalize on it. So here we are. We're going to do this same pullback strategy, the development of which is already done. And let's see here. All I got to do is write down what dx is. Right now, notice not ds. We don't have ds anymore, thus calling this a vector line integral. Right? If it was ds, it'd be a scalar line integral. So I don't even have to write down ds. I only have to write down dx. And dx is v vector dt. Displacement is velocity times time. No ds to deal with. x position, where I am, right, is a function of time. That's it. Everybody on board? Let's see an example. Okay, so let's suppose that you're walking outside, you're walking in the wind, and the wind's blowing around, but because of where certain buildings and trees and such are, the wind's not constant. The wind's blowing in different directions, different places, right? And so here you go. Here's a formula for the force that the wind is applying to you, depending on where you are. So force is a function of position. Okay. And question, how much work do you have to exert in walking counterclockwise along the top half of the unit circle? Let's talk about this curve here, counterclockwise along the top half of the unit circle. Here's a picture. Top half of the unit circle. All right, so that's distance is 1. Let's see. Now, specifically counterclockwise, notice. So we're walking that way. We're not walking the other way. Makes a difference. Okay, so that's what I need to parameterize. Again, just like with scalar line integrals, everything in here, x, how do I rewrite x? Well, it's by way of the parameterization. You've got to parameterize your curve first. So let's do that first. How do we parameterize this curve? Again, easy. Well, I kind of got ahead of myself there. But it's an easy parameterization. X is just cosine t sine t. Right, and everything we're going to write down is going to come out of that, yeah.
You would walk clockwise with the negative cosine t?
That's a great question. I'm going to get to that in a couple of minutes. Yeah, fantastic. I'm going to spend about a page of lecture notes answering that question. Yeah, great question. Okay. Okay, so, yeah.
Did you calculate the force that you need to use to overcome the wind?
Yeah, that's the next thing I'm going to do. Yeah, y'all are predicting the lecture. That's great. Okay, so let's, so the first thing we have to talk about here, this is a physics thing. This isn't a physics course, but gosh, this is so hard to not talk about. We've got to do at least a little bit of this. So the integrand is negative f, not f. And let's talk about why that is. Why is it negative f? And it has to do with sort of equal and opposite forces. Has everybody had a physics class, by the way? Just curious. Show of hands. Okay, good. Okay, so most of you have. If you haven't had a physics class, no worries. The idea, it's actually a pretty straightforward idea. If I'm holding up this stylus here, right, there are actually two forces involved. The two forces are exact opposites of each other, and they have to be exact opposites because they add up to 0. I know the forces add up to 0 because the stylus is not accelerating. Right? F equals ma. If the total force wasn't 0, the acceleration wouldn't be 0. So it's not moving, forces are 0. So what are the two forces? Well, one, the stylus is applying a force downward to my hand. Right? Gravity is pulling the stylus downward. My hand is applying a force upward. If it were not for my hand applying the force upward, this stylus would be accelerating downward. Right? So what we have is two exact opposite forces. Opposite because they add up to 0, therefore they're negatives of each other. Right? So you got to think in terms of, when someone gives you a force, which of the two forces are they giving you? Are they giving you the force that, let's say, gravity is applying to the stylus, which is downward? Or are they giving you the force that we are applying to hold up the stylus? So they're opposites. So you got to pay careful attention to the language. And here the language is that F is the force that the wind is exerting on me. You. Right? So how much force are we exerting back to keep from falling over, which of course is the point of applying a force in the wind, right? We're applying the opposite force. So since the question was how much work do you exert, how much work you exert relates to how much force you are pushing with. And so you need the negative of the given force. Is everybody on board with that? It's a little physics little thing there. Okay. All right, so be careful with that. So here's the force that I'm applying. It's negative F. But other than that little twist, work is a vector line integral of force dot dx, just like it was in our developing example. Everybody good so far? Okay. All right. So here's that parametric curve. Of course, we talked about that. Now, careful. This parametric curve only goes halfway around because this is the top half of the unit circle, not the full unit circle, just the top half. Okay. So there's our parametric curve. T goes from 0 to pi, not 2 pi. Is everybody on board? Okay. Derivative gives me the velocity, right? And now we have all the tools that we need. Dx is velocity times dt. F, okay, let's be careful with this one. Our integrand of negative f, right? Don't forget f is y comma negative x. So negative f is negative of y comma negative x. It's by the way, it's easy to get lost in the minus sign, so do be very, very careful. Notice I've kind of I could have just written down negative y comma x. Here I've sort of put one extra step in there so I could more visibly see, as I was writing down the algebra, I wanted to be able to see that minus sign in place before I actually do what it does. Okay. Okay. Oops. And let's see, our parameterization, y is sine t. X is cosine t. Note the canceling minus signs. Everybody happy? Okay. And now I've got a single variable integral. This, at a glance doesn't look like a single variable integral because there's vectors and a dot product, right? But don't forget a dot product is just a scalar. So this whole dot product is this scalar value that you get from multiplying out. We get lucky here, Pythagorean identity. That simplifies very nicely. And so we get an easy integral and thus an answer. Everybody happy? Yep.
Is the force negative F specifically because the wind is in the exact opposite direction?
Yeah, so here's me, right? The wind is blowing on me like this, and this is this is F, right? What was given in the problem is F. The question asks, how much work do I have to exert? Well, I'm going to lean in. I'm going to be pushing that way. So, because if I didn't lean in, if I just stood there thoughtlessly, right, the wind would just blow me over. Right?
But if
yeah. So I'm applying a force that's like that, and that's the negative of the given force. Yeah.
But if you were walking on like a different path, then it would be like a different angle.
Well, no, so I'm always going to be leaning exactly opposite of the wind, right? And so we're ignoring here, the extent to which I'm accelerating as I, run around the curve and stuff like that. Here, I'm just, slowly walking, and the forces of acceleration are negligible. Yeah. Is that what you were wondering about, kind of? The sort of other forces of, like, how I move?
No, I was wondering, like, the direction that you're moving in is always...
Yeah, so the direction gets accounted for in the displacement vector. Right? That's where that shows up. Yep. Does that make sense? Anybody else? Okay. All right. Okay, so question from over here earlier. What if you're going the other direction, right? So you're going that way along the curve instead of that way along the curve. And these are two different curves in terms of work calculations, right? mean, here's an easy, if you're not entirely sure why this should be, which is easier, climbing up some stairs or climbing down the stairs, right? This is pretty different experiences, right? So opposite directions along what is ultimately the same underlying set of points, yeah, right? But the direction is highly influential on how you experience the work. Okay. All right. So there's a couple of different ways that you can answer this question. I'm going to give you 4 different answers, 3 of which are acceptable. All right? Okay. So here's the first way you can think about it. So I want to parameterize this curve. So step 1 is just parameterize this curve and plug and chug, just like on the previous page. I just, have to ask now, how do I parameterize this curve? How do I get at that I am starting here as opposed to starting here? Well, I'm just going to reconceive of how this angle T shows up in this question. I'm going to think of T as being that angle. Right? If T is that angle, and let me zoom for, if T is that angle, then look, when T is 0, you're here, and then as T increases, you move in the correct direction around the curve. Does that make sense? Okay. All right. Now if that's T, then that means that our usual, what you might call our polar theta is pi minus T. Right, so position is cosine theta sine theta, as always. Just making sure that you interpret correctly what theta is. Theta here is pi minus T, and so you get those formulas. And then don't forget your angle addition formulas. Right? Hope everybody remembers angle addition formulas and symmetries of trig functions and that kind of thing. This simplifies to that. So, let me do that in green. So there's the first way that you can parameterize this curve. How y'all doing on that? Is everybody okay with that? Okay. Let me show you the second way to parameterize this curve. This is part 2 of option 1. Second way you can parameterize this curve is to just notice that as you go, as intended here, clockwise along this curve. As you go, you are going exactly the mirror image of the parameterization on the previous page. This one we already know. That one here is cosine t sine t. Right? The green parameterization that I want is exactly the mirror image over the y-axis of cosine t sine t. And reflecting over the y-axis gives me a minus sign on the x-coordinate. Right? So I take my blue curve, cosine t sine t, reflect with that minus sign, and the result is my green curve. That's a different way to think about it. I know you might like that more, you might like that less. It's different point of view. Yep.
In option 1, choosing T as an angle that we normally, because we usually go from the X to that doesn't matter.
It's fine. I mean, I'm calling it T. I'm not calling it theta and then invoking standard polar coordinates formulas, right? So, and notice very specifically in the discussion, I was referring to this as my theta, right? And that is the standard polar coordinates angle, measured counterclockwise from the positive part of the x-axis. So you can label T anything. If you want to create an angle and call it S, you can make it whatever you want, whatever's convenient for your purposes. Just be very clear about what it is, and then solve as necessary to relate it to whatever convenient things you might want to work with. Here, I think this theta here was just more convenient to work with because known existing parameterization from polar coordinates. Okay. Anybody else? Okay. All right. Okay. So and then everything follows from here. Once you know the parameterization, dx is v dt and all that, and blah blah blah, and you guys can fill in those details. And by the way, the answer ends up being negative pi, which is, how about that, the exact negative of what we got before of positive pi. Okay. All right. Okay, now I'm going to show you two more ways of doing this problem, one of which is acceptable. Here's this third one. This is the final acceptable method here that I'm going to show you anyway. There may be others I just haven't thought of. And that is to think about the Riemann sum itself. I mean, keep in mind we've got this curve. Going along, and we're taking this curve and chopping it up into pieces. Right? And if you're going clockwise, then, well, this is what it looks like when you chop it up into pieces. If you're going counterclockwise, well, this is what it looks like when you chop it up into pieces, right? You're still adding up over the same little pieces of curve. The only difference is between the two is on this little piece. When you're going clockwise, that's your displacement. And when you're going counterclockwise, that's your displacement. And those displacements are negatives of each other. So you can just think of these integrals as Riemann sums and observe that these two Riemann sums are identical everywhere. You're adding up on all of the same pieces with all of the same forces at all of those same locations and then dotting them with the only things that are different is displacement differentials that are exact negatives of each other. And so from this Riemann sum point of view, your answer has to be the negative of the previous example. So this, to answer your question, yes, when you go two different directions along the exact same curve, through the exact same force field, the work integrals are exact negatives of each other. Yep, that's a good insight. Everybody happy with that? Okay. All right, now let me show you number 4, and this one's not acceptable, at least in my class. So a lot of students say, oh, let's see here. I want to walk clockwise. Okay, here's how I'm going to walk clockwise. I'm going to walk clockwise by parametrizing like this, and I have t start at pi, and then I'm going to have t end at 0, right? And the rationale is that, well, look, I parameterized the curve. There's the curve, and I want to start here. Well, that's where t is pi, and then I want to end here. That's where t is 0. So t goes from pi to 0, and then you write down, morally equivalent. Right? You write down this integral, except instead of from 0 to pi, you write down pi to 0, and then calculate from there. Now let me explain why I don't like that. This setup requires the reader to believe that we have established clear rules on how the universe works when time goes backwards. And I am not comfortable with this, right? Everybody see what I'm talking about? I think they're making stuff up. Okay? So, now it is true that you get the numerically correct answer, but again, keep in mind, this is not a class about answers. This is a class about clear mathematical reasoning, right? And I'm willing to accept certain things about physics that we understand, etc. But time going back, this is not a science fiction movie, right? So I don't know, what does the student mean when they say, oh, time, goes backwards from pi to 0. I'm out. I don't know. This doesn't make any sense. You're making stuff up. Does everybody see my complaint? Okay. So you got 3 alternatives that are all fine. So please don't do this one. Now, you'd probably get some partial credit if you do something like this. Certainly, if you write this down, there's a lot that is correct. Namely, you've gotten the force correct. If you do all of this business down here, you've done the pullback correctly. You'd get partial credit, but the setup is not, in fact, particularly realistic, and so you definitely lose some points. Okay, all right, I'm out of time. See y'all later. Have a great weekend.
I